Hello everyone! In this video we are going to talk about the TB6600 stepper driver. Many people say this driver is easier to throw away and replace with a proper one. But finding a high quality driver in a compact size is not that easy. And I definitely don't want to mount a driver the size of a headstock on my small lathe. So in this video I'll try to understand what's wrong with my driver and how to fix it. Let's start by identifying the problem. I've already used this driver on my lathe, so I know how it behaves. I'll set the peak current to the maximum, which is 4 amps. I also set 1/32 microstepping. As you can see, all deep switches are set to off. That means maximum current and the highest microstepping setting. Let's connect the driver to the lathe and see how it performs. The carriage moves with slightly higher friction closer to the tailstock. At some point, the motor starts skipping steps. I spent some time calculating the required torque to make sure the motor would have enough margin to move the carriage. I am confident in my calculations. I installed an EMA23 motor, model 57HS56, with a rated torque of 1.2 Nm. At first, I thought the problem was the low supply voltage of 16 volts. But after increasing it to 22 volts, the torque did not increase at all. Alright, let's measure the motor torque. I will use a 135 mm wrench as a lever and a regular household scale. I'll rotate the screw until the motor starts skipping steps. From the video, I saw a peak value of about 240 grams on the scale. It's easy to calculate the torque in Newton meters. I got 0.32 Newton meters. That is very far from the rated 1.2 Newton meters. And this is with the current set to the maximum of 4 amps. You can clearly see how little force it takes to move the motor by hand while it's holding position. Let's open the driver and look inside. Just a couple of screws. There is an aluminum block mounted on the heatsink to transfer heat from the driver chip. Originally, it was glued to the chip with some unpleasant adhesive. There was no thermal paste between the block and the heatsink at all. I sanded the surfaces and applied proper thermal paste right after buying the driver. The chip in my case is marked S109AFTG. The full name is TB67S109AFTG. It looks reasonably well made. Hopefully, it is genuine Toshiba chip. The second important parts to check are the optocouplers. On step input, there is a high-speed 6N137 optocoupler rated up to 300 kHz. That's good. On the direction and enable inputs, there were originally PC817 optocouplers. I replaced them with PS2561 while solving another issue, but that's not important right now. Now I want to measure the actual motor current. I also want to measure the reference voltage that set the motor current. There are two current sense resistors on the board rated at 0.22 ohms. By measuring the voltage drop across them with an oscilloscope, we can calculate the actual current through the motor. I soldered two wires to the resistor to connect the oscilloscope. Reference voltage can be measured from the lower side of this capacitor. Ground can be taken from the upper side of the same capacitor. I'll also solder wires for convenient measurements while the driver is assembled and powered on. Now I reassembled the driver with the wires sticking out. I spread the remaining thermal paste just to make it work somehow. Since I will measure the current in one winding and I need the maximum value, I'll disable microstepping. That means setting the first two switches to on. If I understand correctly, in this configuration, both windings will have the same holding current regardless of rotor position. The current setting remains at maximum. I mount the driver and measure reference voltage first. Power on, hopefully nothing burns. I see 1.7 volts. Good. Now I connect the oscilloscope to the sense resistor and adjust the settings. One vertical division equals 0.2 volts. I see about 0.33 volts peak. Good. Let's calculate. Reference voltage is 1.71 volts. The voltage drop is 0.33 volts. The sense resistor value is 0.22 ohms. According to the datasheet, the formula for the motor current looks like this. Now I put in my numbers and calculate. The calculated motor current from the reference voltage is 1.55 amps. The measured current can be calculated using Ohm's law. 0.33 divided by 0.22 equals 1.5 amps. The measured current matched the value from the datasheet formula, so we can see that the formula works correctly for this chip. And here is the answer. Even though I set 4 amps, the real motor current is only 1.5 amps, about half of what this motor should have. So I need to increase the reference voltage. I will rewrite the formula from the datasheet to calculate the correct value. To get a motor current of 3 amps, the reference voltage should be around 3.3 volts. To get 2.5 amps, it should be about 2.75 volts. My friends told me that to be a real YouTuber, I need an electric screwdriver in the frame. What do you think? Does it look modern enough? I would make it 5 times faster, and it definitely needs a magnet. I removed the extra wires. The oscilloscope is no longer needed. Reference voltage is set by these resistors depending on the dip switch combination. The circuit looks roughly like this. Basically, it is just a voltage divider. If I reduce the upper resistor value, reference voltage increases. I will replace it with a 10 kΩ trimmer and adjust it manually. Important note: I should set it to maximum resistance first. If it goes to 0 ohms, reference voltage will jump to 5 volts and the chip will most likely burn. I reassemble the driver. The electric screwdriver must stay in the frame. I switched the microstepping back to the 1/32. Current is still at maximum. Power on. Nothing exploded. Good. Reference voltage is 1.28 volts. I need 3.3 volts for 3 amps. I reduce the resistance. Reference voltage increases. I set 3 volts for now, which is about 2.7 amps motor current. Now I test the torque again. I see 488 grams on the scale. That equals 0.66 Newton meters. Better, but still not great. I increase reference voltage to 3.3 volts. Now I see 556 grams on the scale. That equals 0.76 Newton meters. I will stop here. I don't want to run the driver at the absolute limit because its cooling is not very good. and the torque has already increased about 2.5 times. That should be enough. I will leave it for 30 minutes to check the temperature. The heatsink temperature is about 55 degrees Celsius. Then I moved the carriage to check if the motor would skip steps with the driver heated. It didn't skip, so there is no overheating. Now I remove the measurement wires. I measure the trimmer. It is 1.76 kiloohms. I will find a fixed resistor with a close value. I managed to get a 1.8 kiloohm resistor. That's very close to what I need. My resistors are much bigger in size, but I still managed to solder it in. Now I will check that everything is soldered properly and there are no missing contacts or shorts. Here is the final result. A close-up of the board may be useful for someone. I clean off the old thermal paste and add the new. I reassemble the driver. The electronic screwdriver stays in the frame. But I don't trust it, so I also tighten the screws with a regular screwdriver. It is important to know that now the current shown on the table doesn't match the real current, just like before, but earlier it was always lower than the table indicated. Now there are settings where the driver current is actually higher than the table shows. I need to keep that in mind. For example, 1.2 amps setting actually gives about 1.6 amps through the motor, and the 1.7 amp setting gives about 2 amps through the motor. Now the driver works. Am I happy with it? Is it a good driver? Probably not. I don't think it is normal to fix a finished product with a soldering iron just to make it work properly. But I already bought it, and honestly it was interesting. I did not change the wiring, the mounting, or install a larger driver. Nothing extra sticking out of the lathe. Maybe you know a high quality compact driver that can deliver up to 4 amps? Leave a comment below. If not, I will just buy the TB6600 again. Try to stop me.